Today, let's learn the maximum and minimum values of a function together. Someone may not be unfamiliar with this knowledge. In junior high school, we learned the maximum value of quadratic functions. As shown in the graph, the function fx is equal to the image of x squared, and it has a lowest point of 0, 0. So how can we use mathematical language to describe that the function value at this point is the minimum value? Fx is greater than or equal to 0, and it holds for any x belonging to R. So how can we explain that it holds true for any x belonging to R? What we see is that the function values in this part of the function graph are all greater than or equal to 0. So, may there be function values smaller than 0 in the parts we haven't seen? How to explain? We can take advantage of the monotonicity of functions, and in the interval from -infinity to 0, the function fx is monotonically decreasing when it equals x, so we can obtain that when f is less than or equal to 0, fx is greater than or equal to fo. Similarly, from 0 to +infinity, the function monotonically increases. When x is greater than or equal to 0, fx is also greater than or equal to 0. In this way, we obtain that for each independent variable x in the domain, its function value is greater than or equal to fo, which is 0. In this way, we say that when x equals 0, the function takes its minimum value, which is 0. In this way, we describe the minimum value of the function from a numerical perspective. Let's review our research process together. From form to number, we first visually observe the minimum value of the function from the graph, and then express it rigorously in symbolic language. We know that the graph of a function y equal to fx is as shown in the figure. So, is the vertical axis of the highest point in the graph the maximum value of the function? Since what we see is a part of the function graph, we cannot determine whether it is the maximum value of the function. We need to consider the domain and monotonicity of the function and argue from a numerical perspective. It can be seen that it is necessary for us to study the maximum value of a function from a numerical perspective. Can you explain the meaning of the maximum value of function fx using the example of y being equal to -x squared? From monotonicity, we can easily obtain that for any x belonging to R, fx is less than or equal to fo. At the same time, it also satisfies that when x is equal to 0, its function value fo is equal to 0. That is to say, if the first condition is met and all independent variables x in the domain have function values fx less than or equal to 0, and there exists a point where x is equal to 0, at which point the function value is equal to 0, then we say that 0 is the maximum value of this function. On this basis, can you give a general definition of the function y being equal to the maximum value of fx? We set the domain of function fx to I. If it has a maximum value m, what conditions does m need to satisfy? Based on the analysis just now, we know that firstly, it must satisfy that when any x belongs to I, the corresponding function value fx is less than or equal to m. At the same time, there exists an independent variable xo in I, whose function value is equal to m. In this way, we give the definition of the maximum value of a function. Generally, let the domain of the function y equal to fx be I. If there exists a real number m that satisfies any x belonging to I, fx is less than or equal to m. The second condition is that xo belongs to I, so that fxo equals m. Then we call m the maximum value of the function y equal to fx. Now let's analyze these two conditions in the definition. Can the first condition fx in the definition be written as fx less than or equal to m? No, because not all function values can be less than m. There must be a point where the function value is equal to m. So, if the first condition is met, fx is less than or equal to m, does it guarantee that at least one independent variable in the domain has a function value equal to m? Is the second condition in the definition essential? If the first condition is met, fx is less than or equal to m, does it include at least one independent variable corresponding to a function value equal to m? Is condition 2 in the definition essential? Let's first take a look at what fx is less than or equal to m. Fx is less than m or fx is equal to m. If either of them is met, fx is less than or equal to m. That is to say, when fx is less than m, it meets the condition that fx is less than or equal to m. Let's give an example from daily life. For example, if all the students in our class are less than 3 meters tall, can we say that all the students in the class are less than or equal to 3 meters tall? This is possible. It meets the first condition. So, is 3 meters the maximum height for our classmates in the class? Obviously not. Let's take another look at the example of our function. For the function f(x) equal to x, the domain is -1 to 2, and it is a closed interval. Is it true that for any x belonging to -1 to 2, f(x) is less than or equal to 4? Clearly established. So is 4 the maximum value of the function? Obviously, this is not. Let's take another look at the function f(x), which is equal to x, and x belongs to the open range of -1 to 1. Does it satisfy that any x belongs to -1 to 1 and f(x) is less than or equal to 1? Is 1 the maximum value of this function if it holds true? No, it can be seen that in the definition of the maximum value of a function, both conditions are indispensable. Can you follow the definition of the maximum value of a function and provide a definition that y equals the minimum value of f(x)? Generally, let the domain of the function y equal to f(x) be I. If there exists a real number smaller than m, and the first condition is satisfied, where any x belonging to I has f(x) greater than or equal to m2 and xo belongs to I, such that f(xo) equals m, then we call m the minimum value of the function y equal to f(x). We further understand the definition of the maximum and minimum values of a function based on its definition. Does every function have a maximum and minimum value? We can look at this familiar linear function, f(x) equals x, and if the domain is R, it has no extremum. Then f(x) is equal to 1x, and it is obvious that this function does not have a minimum value, indicating that the minimum value of the function does not necessarily exist. Okay, let's take another look. If a function has a maximum value, how many do they have? We believe that the maximum value of a function is a holistic concept, and if it exists, it must be unique. It is the largest value among all function values, but there can be multiple independent variables when taking the maximum value. For example, when the function f(x) is equal to x squared and x belongs to the closed interval -2 to 2, we can see that the maximum value of this function is 4. When the function value is 4, the corresponding independent variable x has two values, positive and -2. Now we will calculate the maximum and minimum values of the following functions based on their definitions. Firstly, the first f(x) is equal to 3x plus 2. X belongs to the closed range of -1 to 2. We know that this function monotonically increases from -1 to 2. So when x equals -1, f(x) has a minimum value, which is -1. When x equals 2, f(x) has a maximum value of 8. The second function. This function monotonically decreases in the range of 1 to 2, so when x equals 1, the function has a maximum value, which is 1. When x equals 2, the function has a minimum value, which is half. In real life, there are many questions about the optimal value of a function. Let's take a look at this question. Chrysanthemum fireworks are one of the most spectacular fireworks, and they are usually manufactured with the expectation of bursting when they reach their highest point. If there is a functional relationship between the height h of fireworks from the ground and time t, when is the best time for fireworks to burst after they burst out? What is the height above the ground at this moment? Let's take a look at this function relationship, which is a quadratic function graph and a part of a quadratic function. We can clearly see that the vertex of the function graph is the highest point where the fireworks rise, and the horizontal axis of the vertex is the optimal time for the fireworks to explode, while the vertical axis is the height from the ground at this time. This way, we can use the knowledge of quadratic functions to solve it. According to the knowledge of quadratic functions, when t is equal to -2 multiplied by -4, 9, 14, 7 and equals 1.5, the function has a maximum value, and the value of h is 29. So the fireworks burst for 1.5 seconds, which is the best time for it to explode, at a height of about 29 meters above the ground. Let's take a look at this function. It is known that the function f(x) is equal to 2 over x minus 1, and x belongs to the closed interval of 2 to 6. Find the maximum and minimum values of the function. This function is not the linear function, quadratic function, or inverse proportional function that we are familiar with. So how do we study it? We observe the structural characteristics of this function. f(x) is equal to 2 over x minus 1. It is closely related to the inverse proportionality function f(x) that we have learned, which is equal to 2 over x. And the function f(x) is equal to 2 over x, and we know that it monotonically decreases over the interval 2 to 6. So let's guess if this function is also monotonically decreasing in the interval 2 to 6. If our guess is true, then the fx image should roughly look like this. Monotonically decreasing from 2 to 6. The function takes its maximum and minimum values at the two endpoints of the interval. This is just our guess. Now we want to prove that the function fx monotonically decreases on the interval. According to the method we learned earlier to prove the monotonicity of a function, if x1 and x2 belong to interval 26 and x1 is less than x2, we can subtract fx2 from the difference fx1 to obtain this equation. Because x1 is less than x2, x2 minus x1 is greater than 0. x1 and x2 are both within the range of 2 to 6, where x minus 1 is greater than 0 and x2 minus 1 is greater than 0. In this way, we get fx1 minus fx2 greater than 0. fx1 is greater than fx2. In this way, we prove that the function fx monotonically decreases over the interval 2 to 6. Therefore, it takes the maximum and minimum values at the two endpoints of the interval. When x equals 2, the function has a maximum value, which is 2. When x equals 6, the function has a minimum value, which is 0.4. Let's take a look at the solution to this problem. We can use the monotonicity of a function to find its maximum value, but when doing so, we must first prove the monotonicity of the function in order to demonstrate that the function has its maximum value at the endpoints of the interval. Pay attention to the standardization of problem solving. Okay, let's review the content of this lesson. Please think about the following questions. Firstly, the definition of the maximum and minimum values of a function. Taking the maximum value as an example, it must satisfy two conditions. The first condition is that the function value corresponding to all independent variables x in the domain should be less than or equal to m. The second condition is that there must be an independent variable xo in the domain that has a function value equal to m. Both of these conditions are indispensable. In addition, the maximum and minimum values are a holistic concept that may not exist, but if they exist, they must be unique. Secondly, let's think about the method we learned to find the maximum value of a function. For functions that we are familiar with, such as linear and quadratic functions, we can use function graphs to find the maximum value of the function. For unfamiliar functions, we can use the monotonicity of the function to find its maximum value. It is necessary to first prove the monotonicity of the function, and then explain that the maximum value of the function is obtained at the endpoints of the interval. That's all for today's class. Goodbye.